Welcome to This Explainer, where we're going to break down the absolute bedrock of modern macroeconomic theory. Today, we're stepping right back into the classroom to dissect the simple Keynesian model and its incredibly powerful mathematical multipliers. You know, this is the exact math policymakers are looking at when debating real-world legislation like stimulus checks or massive infrastructure bills. If you've ever wondered how a single dollar spent by the government, or even a private business, can ripple through the entire economy to create a much larger wave of total income, well, you're definitely in the right place.
Here's our roadmap for today. We'll start with the Keynesian cross model, move right into the investment multiplier, explore the government purchases multiplier, calculate the tax multiplier, and finally unpack the slightly counterintuitive balanced budget multiplier.
Okay, Section 1. The Keynesian cross model, the foundation of aggregate demand.
During the Great Depression, John Maynard Keynes completely revolutionized economics by asserting something that really challenged classical thought. He argued that low aggregate demand, not just the supply of labor and capital, is what actually drives economic downturns. But to understand this mathematically, we have to start with human behavior. This quote captures Keynes's fundamental psychological law regarding how people actually behave when they earn an extra dollar. Think about it. When you earn an extra buck, you don't just lock the entire thing in a vault, right? But you also don't spend every single penny of it. You typically spend some of it, and you save the rest.
So the crucial point here is this concept of the marginal propensity to consume, or the MPC. The MPC is the absolute bedrock variable upon which every single multiplier calculation we're going to do next depends. For example, if your MPC is 0.8, it means for every extra dollar you earn, you spend 80 cents and you save 20 cents. That simple, continuous feedback loop between income and consumption, that's the engine that gives fiscal policy its real power.
Moving on to Section 2, the investment multiplier, volatility, and output fluctuations.
Historically speaking, investment is the absolute most volatile component of GDP. Notice how the downward-sloping investment function shows that as the real interest rate rises, borrowing costs go up and the quantity of investment demanded drops. But here's the big question. What actually happens to the broader economy when investment suddenly drops? And not necessarily because of interest rates, but maybe due to an external shock or just a sudden loss of business confidence. Well, because of the MPC, that initial drop is definitely not the end of the story. Think about it like this. If a company suddenly cancels a big factory build, those construction workers lose income. And because those workers have an MPC, they immediately cut back on their own spending. Maybe they skip going to their favorite local restaurant. Now the restaurant owner loses income, and so they cut back on their spending. It's a domino effect. An initial drop in investment drives equilibrium income down even further in a massive multiplied effect. This multiplier is really just a formal way of explaining why output fluctuates so drastically during the typical business cycle.
All right, Section 3, the government purchases multiplier, fiscal policy in action.
Knowing how volatile private spending affects income, we really have to ask, how does the economy respond when the government deliberately steps in and increases its own purchases to stimulate growth? Notice the initial increase in government purchases, represented by the upward shift delta G. But look closely. The resulting increase in total output and income, delta Y on the horizontal axis, is clearly wider than that initial vertical shift. The resulting change is actually larger than the initial injection. It's pretty wild to see it visualized. So how exactly does that happen? Well, we can actually track that initial government dollar as an infinite geometric series. Say the government spends $1 buying a bridge from a contractor. The contractor pays their worker, the worker takes that income and spends a fraction of it, determined by their MPC, remember, at the local grocery store. The grocer then spends a fraction of that income, which is the MPC squared, and so on, cascading through the economy. Mathematically, if you actually sum up that infinite geometric series of spending, it simplifies elegantly into this beautifully simple formula, 1 over 1 minus MPC. This gives us the exact, precise ratio of how much total income changes for every single dollar the government spends. Let's put some concrete numbers to this theory to make it real. If we assume our marginal propensity to consume is 0.6, meaning people are spending 60% of any new income, we just plug that right in. 1 minus 0.6 is 0.4, and 1 divided by 0.4 gives us a multiplier of exactly 2.5. Think about what that actually means. A $1 increase in government purchases eventually raises the total equilibrium income of the economy by $2.50. Talk about a real return on investment.
Which brings us to Section 4, the tax multiplier, altering disposable income.
Now that government spending effect is incredibly powerful for sure. But what if the government alters taxes instead of buying things directly? Comparing these two formulas side by side immediately reveals two major differences. First off, the tax multiplier is negative. And that totally makes sense, right? Because income moves in the opposite direction from taxes. Raising taxes lowers your disposable income, which therefore lowers spending. But second, notice the numerator. It's not a 1 anymore, it's the MPC. Because the MPC is a fraction less than 1, the tax multiplier is always going to be smaller in absolute magnitude than the spending multiplier.
Returning to our real-world example where the MPC is 0.6, if we plug that into the tax multiplier formula, we get negative 0.6 divided by 0.4, which equals negative 1.5. So, a $1 cut in taxes raises equilibrium income by only $1.50. Notice that is a full dollar less of economic stimulus compared to a $1 increase in direct government spending. Why is that? Well, because when the government cuts taxes by $1, consumers save a portion of that initial dollar before injecting the rest into the economy. Direct government spending, on the other hand, injects the full dollar immediately.
And finally, Section 5, the balanced budget multiplier, the counterintuitive policy.
This brings us to a really fascinating thought experiment, and it's one that honestly often surprises people. What happens if the government increases its spending to stimulate the economy, but decides it absolutely doesn't want to run a deficit? What if it raises taxes by the exact same amount to pay for it, so the budget remains perfectly balanced? The somewhat counterintuitive mathematical answer is exactly 1. The equilibrium output rises by exactly the initial increase in government spending, and no more. A balanced budget expansion is literally still expansion now.
Breaking down the exact math really illustrates why this happens. You essentially have two forces acting at the exact same time. You have the positive stimulus of the direct government spending multiplier pushing income up. Simultaneously, you have the negative drag of the tax multiplier pulling income down. But because we just proved that the spending multiplier is always exactly 1 greater than the tax multiplier, the positive stimulus outmuscles the negative drag. The net expansion leaves you with an increase in income exactly equal to the initial spending injection. It's perfectly balanced.
As we wrap up our deep dive today, I want to leave you with a final thought to really ponder. Everything we've calculated today assumes a static model where only income and consumption are moving. But what happens when we zoom out to a broader model where things like the interest rate and money supply can actually fluctuate? How might those dynamic variables alter the power of these multipliers in the messy, complex, real world? It's a critical question, and really mastering the simple multipliers we covered today is the necessary first step to figuring that out. Thanks for joining me, keep exploring, and I'll catch you in the next explainer.